Let's combine the chain rule and the derivative of sine to differentiate a slightly more complicated function. Let's try to differentiate sine of x squared. We can realize this function as the composition of two functions. I can write sine of x squared as the composition of f and g, where f is the sine function and g is the squaring function. Now, how do I differentiate a composition of two functions? I use the chain rule. So I differentiate f, and the derivative of f is cosine x, right? The derivative of sine is cosine, and the derivative of g is just 2x. So now I want to differentiate the composition of f and g, and that's by the chain rule, f prime of g of x times g prime of x. In this case, f prime is cosine, so it's cosine of just g of x, which is x squared, times the derivative of g, which is 2x. So the derivative of sine x squared with respect to x is cosine of x squared times 2x. Honestly, this is a pretty neat example. In magnitude, this function, sine of x squared, is no bigger than 1. And yet, what do we know about this function's derivative? Well, the derivative of sine of x squared is cosine of x squared times 2x, and that function can be as large as you like. You can make cosine of x squared times 2x as big as you want as long as you choose x appropriately. So what we have here is a function which isn't very big. The function's value is no bigger than 1 in magnitude, but the function's derivative is very large. And you can see that on the graph. The values of this function really aren't that large. The values are all hugging 0. But the derivative, the slope of the tangent line, is enormous. I mean, look over here. If you imagine a tangent line, that tangent line is going to have enormous slope. The derivative over here is going to be very large in spite of the fact that the actual values of the function really aren't that large. This actually provides another lesson. Just because two functions are nearby in value doesn't mean that their derivatives are anything close to each other. For instance, here's the graph of the cosine function, and here is the graph of a function sine of x squared over 10 plus cosine of x. Since sine of x squared is between -1 and 1, this differs from just cosine by no more than 1/10. And yeah, you can see the graph is really close to the graph for cosine, and yet this graph is way more wiggly. Let's zoom in and we can see the same sort of thing. Here's a zoomed in copy of just the cosine curve, and here's what happens if you zoom in on this other function. And in terms of the value, this other function really isn't differing from cosine very much. But in terms of derivative, this function is totally different than cosine. This function is super wiggly, so the derivative of this function is enormous, even though the derivative of cosine is no bigger than 1 in magnitude. If you think this is kind of an interesting example, it's worth trying to cook up an even more elaborate example. Here's a very specific challenge for you. Can you find a function f? Just make one up, so that your function's values in magnitude are less than c, and your function's derivative in magnitude is less than c. So I want a specific number c, so that no matter what value of x you plug in, the function's value there and the function's derivative there is less than c in magnitude. But I want that function to have second derivative which can't be bounded by a constant. I want you to cook up a function so that, yeah, the values in the first derivative are bounded by c, but the second derivative can be as big or as negative as I'd like by choosing x appropriately. Can you find a function like that?